I myself Radha, assistant professor working in Rathinam Technical Campus, Department of Computer Science and Engineering. We are going to see about hazards under computer architecture course. Hazards in computer architectures are situations in pipeline processor that prevent the next instructions from executing in its designated clock cycle, reducing performance and potentially causing incorrect results. Primarily, it is categorized into three different hazards. The first one is data hazard, second one is control hazard, third one is the structural hazard. We are going to see in detail. The first one is the data hazards. Data hazards in computer architecture are pipeline stalls caused by instruction dependencies where a subsequent instructions needs data from a prior one that hasn't finished yet, leading to incorrect results. Further, this divided into three different data hazards. The first one is read after write hazard. This one also known as true dependency. This occurs when an instruction needs to write a value that a previous instruction is in process of writing. For example, instruction 1 here R2 and R3 are added and stored in the register R1. The instruction 2 we are going to subtract R1 and R5 and store the result of R4. Here, instruction 2 depends upon the result of instruction 1. So here, read after write hazards happens. The next one is write after read hazard. It is also known as anti-dependency. This occurs when an instruction writes to a register after the previous instruction reads from the same register. This is generally a problem of out of order execution. For example, here instruction 1, we are going to subtract R4 and R5 and store the result in R1. The instruction 2, we are going to add R2 and R3 and store in the register R4. Here instruction 1 needs to read R4 before instruction 2 writes to it. So here right after read hazards happens. The next one is the write after write hazard. This one also known as output dependency. This occurs when two instructions write to the same register. The second instruction must wait right after the first to preserve correctness. This is almost relevant to out of order execution. For example, here instruction 1, we are going to add R2 and R3 and store the result in R1 register. In instruction 2, we are going to subtract R4 and R5 and store the result in R1. Here the final value of R1 should come from the instruction 1. So here right after right hazards happens. So these are the data hazards happen. This one have we have solutions for the data hazard. The first one is pipeline stalling. Here we are going to delay the execution of instructions in the pipeline to resolve the hazard. For example, here R2 and R3 are going to add and store the result in R1 register. The instruction 2, we are going to subtract R1 and R5 and store the result in R4. In this case, instruction 2 must wait for instruction 1 to complete writing to R1 before it can execute. This pipeline stalls for one cycle. This is one solution for data hazard. The second solution is data forwarding, which is also called as bypassing. Data forwarding pass the result from one pipeline stage directly to another without writing it back to the register file. For example, instruction 1, we are going to add R2 and R3 and going to store in R1. In the instruction 2, we are going to subtract R1 and R5 and stored in R4. Here, the result of R1 is forwarded from one execution stage of instruction 1 to execution stage of instruction 2. So, this is one solution for data hazard. The third one is out of order execution. This is also called as code reordering. For example, here instructions are executed as soon as their operands are available rather in strict program order. Here we are going to store the memory into the R1. In instruction 2, we are going to add R4 and R5 and store in R3. Here, instruction 2 can be executed before instruction 1 completes if all its operands are available. So, this is one solutions for data hazard. The fourth one is register renaming. Here, we are going to eliminate false dependencies by using more physical address than architectural registers and mapping logical registers to physical ones dynamically. For example, here in instruction 1, we are going to add R2, R3 and store in R1. In instruction 2, we are going to multiply R4, R5 and store in the result of R1 register. Here R1 in instruction 1 and instruction 2 are renamed to two different physical registers so that we are avoid conflicts. The fifth one is speculative execution. Here, execute instructions based on guesses or predictions about future instructions, data, or control flow. For example, we are going to load value into R1. In instruction 2, we are going to add R1 or R4 and store the value in the register R3. So, in the instruction 2, we are speculatively execute assuming R1 is correct. If we load R1 is delayed, the result add is speculative. So these are all the uh, solutions for data hazard. So the second hazard is control hazards. Control hazards occurs when flow of execution is altered by branch or jump instructions, which makes it difficult to predict the instruction to execute. For example, here we are going to use the branch equal instructions. Here you are going to check R1 is equal to R2. The instruction 2 we are doing addition. Instruction 3 we are going to label. So if the branch is taken, then instruction 2 should not be executed, leading to control hazard. So we have solutions for control hazards too.